Let's see, my friends, if we can get our mind around the concept of a limit even more deeply than we already do. Let's see. I think there's something special I wanted to start with, and now I'm forgetting what it is, but let's do this from yesterday. Let's try to do something from yesterday that we except for let's kind of do it algebraically. And so just to get it, just to have this be a nice looking graph, let's see, let's play around and make our own. Let's see, let's try something simple like x squared and I don't know, minus 4x maybe. And I'd like to slide it up. Let's see, it looks like the bottom of it is at minus 4. And so if I took it up 6, that would put it up there. So, whoa, that was bad, whatever I just did. I don't know what I did, but the graph went away. So let's see, let's find the slope of that when x is 3. That looks like a pretty good spot over there. No, that's 3, 3. We don't want the same x and the same y. Well, we can fix that. Let's make this go up 7. There we go. So take a look at the point 3, 4. And let's see if we can find the slope at that point. But before we do it, I'd like you to kind of take a guess at it. Like, what do you think the slope's going to be there? I'm going to make a copy of it and put it over in our notes because I can. Get over here, you cool graph. Crop. See, I got to keep the x-axis in there, otherwise I won't know where I am. Let's make this dude a little bit bigger. So let's see, I'm at the point 3, 4, and I'm estimating the slope. So I'm going to try to draw, what's this line called from yesterday? And that was pretty good.
Tangent.
Tangent.
Tangent. So, and notice the graph is square. In other words, a distance of 1 and a distance of 1. Like I didn't distort it. If I distorted it, does it make sense that would screw up the way the slope looks? But you take a guess. Like, what do you think that slope is?
Like 2?
Maybe 2, certainly positive, right? So maybe the slope of that is 2, something like that. I am looking a little more carefully now and thinking the gap in the top and the gap in the bottom. The gap in the top is a little, like, I don't think I drew it perfectly. Like it might be a hair steeper than that. But yeah, maybe 2. And I think 2 is a particularly good guess because it seems to cross right there and then it hits our point here. And isn't that up 2 boxes and over 1 box? And so it really does look like 2. If the answer to this is 2, I'm not going to be surprised at all. So now let's try to do this a little more algebraically than we did yesterday. That's kind of where we're trying to go with this. And so let's do something kind of cool here. Let's see. Let me erase some of this stuff because I made a big mess of my beautiful page. There we go. So since we're at the point, so we want to know, let's see, the slope. Can I write on this? The slope at x equals 3. We've estimated it just by look to be at least approximately 2, and we might get lucky and it might really be 2. And because I know calculus, let's see, yep, it is 2. Because I know calculus, it is 2. That was actually a really good guess. And notice how you know, taking the time to draw a good picture and so forth can kind of really help your thinking. And so let's kind of dive into this. And so we have the point, since we're at x is 3 and we plugged 3 in and we found out we're at the point 3, 4, then we just need one other point. And what's important about the other point we choose?
But it's really close.
It's really close. And so let's pick 3.1. That'll probably be close enough, right? So now you go find you find the x or the y that goes with that, and then you go y minus y over x minus x, and see if you get something close to 2. And because of the picture, you darn well should get something fairly close to 2. I'm doing it with you. I got 4.21 for y. And I'd encourage you to always stop and think. Like, the calculator told me 4.21, but before you proceed, like, look at the graph. Does that make sense? Well, yeah, it makes sense because my x is a little bigger, and because of the shape of the graph, then the y should be a little bigger than 4, and so it's bigger than 4 and it's close to 4, and so I know I didn't blow it. Like, so easy to just type something wrong in your calculator, right? So apparently I didn't do that. It's a miracle.
I got 2.1.
Yeah, so now I go, so easy. This is embarrassing. Like, this is a calculus class, and we're just like doing the dumbest, simplest stuff. So easy. Y minus y over x minus x. Justin said he got 2.1. 4.21 minus 4 is 0.21. 3.1 minus 3 is 0.1. Yeah, he's right. We got 2.1. And so this is ultimately an approximation, or from last night's assignment's language, you could say that's the average slope between those 2 points. But we'd like to do better than that ultimately, right? We'd like to get it exactly right. And of course, we're wondering if it is too. But let me show you something extremely cool here. Extremely cool. What if for this second point up here, and I'll draw it pretty far away just so that you can see it, rather than just guessing x to be 3.1, what if we don't even guess? Like, this is what mathematicians hate, guessing. Guessing is for losers. What if we just let it be x, and then let's just make a note to ourselves that x has got to be close, as Eve reminded us. It's got to be close to 3, right? I love drawing clouds around stuff. It's like, makes you want to look at it, doesn't it? It's close to 3. And in my picture, I made it on the high side of 3, but remember, you don't actually, couldn't we choose x to be 2.9? Wouldn't that have worked good too? We don't have to be on the high side of 3, it's just I drew it there. And but a second ago, once we choose x to be 3.1, didn't you put 3.1 into the equation to get y? In other words, if I choose this to be x, then wouldn't I call y, like, I mean, I could say y, that's okay too, but I have a reason for saying f of x here. And so my question is, could we do the same thing? It's just this time we don't have to guess. In other words, in light of this new discovery, so here's sort of our first try. Well, our second try then would be that the slope, and it's kind of easier because you go, well, y minus y, and I think I'll rewrite this just because this is so cool and I don't want you to miss it. And you know, I could call that y. There's no magic in saying f of x. Who cares? It's y. And so wouldn't the slope then be equal to, maybe I'll move that down since what I just did isn't the slope. Don't I go y minus y? That's what I just did, right? It was 4.21 minus 4 over x minus x. It's just that a second ago x was 3.1. I just haven't picked yet, right? So this isn't any different really, except for when you look at that, you should say, well, that's really great, Mr. Math Nerd, but like, what good does that do? That doesn't do any good. Like, it's a big ugly mess. What good does that do? Well, would you also agree that, well, isn't f of x equal to x squared minus 4x plus 7? Like, couldn't I at least replace that? So x squared minus 4x plus 7, there's f of x, and then there's the minus 4. So just so the notes look awesome, I'll say, isn't that f of x? And I can't really do anything to the bottom. And then I guess I could, clean the top up a little bit, like it's x squared minus 4x, but then there's a plus 7 and a minus 4, which comes out to plus 3. And so that's like nicer. But again, what good does that do? It's not like you can look at that and go, oh, yeah, look, the slope is 2.
Can we factor that?
Yes. Now we'll get there in a second, but what I want you to do for a second, just to kind of slow your way to what Vail ultimately just said, which is a good idea, is we want x to be equal to 3, right? But this doesn't help, because what if you put 3 into that, what happens?
Divide by 0.
You end up with 9 minus 12 plus 3 on the top, which is 0. And you end up 3 minus 3 on the bottom, which is 0. And so it breaks. And of course it breaks, because that's having that second point be the same exact point. And so it's like, that doesn't work. That's stupid. That doesn't help. But as I said before, can't you still pick x to be really close to 3? Now let's do that. So let's just make a little chart down here. We love charts. For math people, we love charts. Oops, that's not f of x. We want to pick x to be, since we can't pick 3, we want to pick x to be really close to 3. Well, a second ago, we picked x to be 3.1, and we got 2.1 for the slope, right? So I don't need to redo that, but you certainly could if you wanted to. But now I'd like you to pick 3.01 and put it in, but again, you're putting it into this expression for the slope now, because we made a new formula for it. So let's put 3.01 into that and just see what it produces. And I'm going to do this in kind of a cool way that I'll show you in just a second. But if you get an answer to this, just blurt it out. It's probably going to be close to 2, right? If you don't get close
2.01.
Something weird. What'd you say, Vail? 2.1?
2.01.
01. That sort of feels right, doesn't it? Sorry, I'm thinking Vail didn't screw that up. But again, does x have to be above 3? No. Couldn't it be below 3? Like, try sticking 2.9 in to that. Or let's even go for closer. Like, what about 2.999? Like we want to be really close to 3 here. So, put stuff close to 3 in. I stuck in 2.9 and I got out 1.9. I stuck in 2.999 and I got 1.999. Do you agree this feels like evidence that the slope at x equals 3 is indeed 2? Because we're getting close to 2 both ways, right? Kind of feels like evidence that it's 2. I'm ready to bet, aren't you? How much would you bet that the slope is actually 2? I'm going to go, I'll bet it all. Let it ride. $2,000, whatever I got. I'm letting it all ride. Looks like evidence that it's 2. Now, in the language of mathematics, and what you're going to see in your assignment tonight, this is the way you would write that. You'd say the limit of, well, our expression here, x squared minus 4x plus 3 divided by x minus 3. As x gets really close to 3, I need you to be able to read that, because like if you show that to somebody in your family and say, this is what I'm studying right now, they're going to look at that as though you're in some foreign language, right? And they're going to try to get away from you. Like, what are you doing? What does that even mean? And you should be able to say to them something like, well, that looks complicated, but that's just an expression that I made to find the slope right around 3, right? That's an expression I made to find the slope right around 3. And you'll notice if you try to put 3 into it, it breaks and it gets 0 over 0. So instead, I'm going to let x be really close to 3, like 2.9 or 3.01. And it appears that the answer to that, my friends, is actually equal to 2, not close to 2, but it's actually equal to 2 because it looks like it's getting close to 2 from both sides, right? And indeed it is. We said earlier that when we graphed it, you know, the slope looked like 2. We've played around with it, and yet it's kind of weird because you can't actually put 3 in there, right? Isn't it kind of strange?
Is there a way to find out for sure in case it's like 1.509 and an 8 or something?
Exactly. Now, notice, and this is where, you know, Felix has the mind of a true mathematician, because is there any reason the actual answer couldn't be 2 and 1/967th or something like that? Like there's nothing magic about the number 2. Do you understand that? I mean, that feels like a landing place to me. Like I feel all happy. It's like, oh, 2, good, that's a nice whole number. But math doesn't care. Like 2 and 1/967th is a number as well, and it's just as legit of a number. And so, is there any reason it can't be? Well, because this is, well, I don't know, think about this. What are we studying right here? We're studying a parabola. Like this is the simplest equation I could possibly make that doesn't have a boring slope. In other words, a line, no matter where you go on the line, it has the same slope. And that's what you knew before you got into calculus. And now we're saying, well, let's look at something that's curved. Well, what's the next easiest equation I could possibly invent? Well, instead of an equation like y equals 3x plus 1, which you may remember is a 1-degree equation because it's x to the first, well, I jumped to x to the second. I didn't make it x to the 19th, or I didn't pick up natural log. Like, don't those all curve too? All the other functions we have to study all have curves to them. Sine has a curve, and so, you know, those are complex types of functions. I picked x squared, and therefore the answer to this one is 2. Because it's really simple. But if this was natural log of x or something like that, we are going to get answers like 2 and 101/967. So in this case, it really is 2. But we don't really know that yet. You need to understand that. In a technicality, we don't actually know. You're exactly right, Felix. Is there a way to kind of, you know, prove it's exactly 2? And that's the sort of the devil in the details business. If somebody said, what's the slope of this curve near 3? And you just said, hey, it's approximately 2. That's like close enough, right? How much money do you need to, you know, buy this car? Well, approximately $2,000. Most of life approximate is good enough, right? And notice our answer is, if you will, within 1/1000th here, right? Like, you know, relax, close enough. This is why people kind of hate math. The devil's in the details. If you actually want to get it exactly right, that's going to be hard for natural log and exponential functions and so forth. And that's actually what fills up the majority of this course, is the fact that you let it bother you that it isn't perfectly 2 here. You don't need calculus to do calculus. Calculus 1 is find the slope of a curve any place you want to be. That's it. That's the entire class. And you can do it by doing what we just did right here. Just find 2 points that's close, write down an estimate, you're done. We're done. The class is over. If you decide you want to get it exactly right, because you're a true mathematician, or because you say, well, as many of you said, well, I got to be in engineering and they want me to take this class, and I'm going to fill up the other 10 weeks with all the details of how to get it exactly right. Like, that's all that exists. But please don't misunderstand this course, because it's going to turn into finding the slopes of crazy curves, and you're going to forget what you're even doing. But the very last day of this class, we're still just going to be finding the slope of a curve. It really is that simple. And you can do it right now. So, would you agree? So I'm going to say something to you now about Monday's discussion, section 2.3. I'm going to steal some of my thunder. You're not supposed to know this yet, but it's kind of cool, and I just can't help showing it to you now. This expression right here for slope, and notice this is a fraction. Slope's always a fraction, right? Because it's y minus y over x minus x. Like, this expression is a fraction, and because we're after slope, it'll always be a fraction. That expression right there will not let us plug 3 in, right? Because it breaks and it's 0 over 0. But Vail noticed something cool, or at least he asked a question. I don't know if he noticed it, but he wondered, is there a way to like put 3 into that? Well, do you notice this top expression factors? What does that factor to?
X minus 3 and x minus 1.
X minus 3 and x minus 1. He's right. And again, this is one of those algebra concepts, like, you better be good at factoring. Are you? Yes, no. Why is that extremely cool? That not only did it factor, but what really cool just happened with that factoring?
Now we can
That's-
cancel like pairs.
So this fraction actually simplified. In other words, it's kind of like if I told you, hey, you have the fraction 21/7, because you guys know math, you'd be like, why are you telling me that in such an ugly, ridiculous way? Why don't you simplify that to 3, right? Don't call it 21/7, call it 3. Well, you didn't notice it right off the bat, but isn't this expression here like 21/7? It's no different. It's the same exact thing. Why does it simplify? Well, why do these two simplify? Because 21 is 7 times 3, and then those cancel, and the answer is 3, all right? They have a 7 in common. You were not able to look over here and go, hey, look, those have an x minus 3 in common. That's hard to do. But if you factor it, that's exactly what happened. In other words, this simplified to a whole number. In other words, it wasn't a fraction anymore. And isn't that what happened over here? It's like it's not a fraction anymore. Why is that extremely cool? Not just so much as like, oh, it's simplified. Good, great. Why is
Because now
that
we
really
can
cool,
put
though?
3 in.
Now there's no reason you can't put 3 in. You understand that? And if you do put 3 in, what do you get?
2.
You get 2. So the slope is exactly 2. So it turns out, like, and again, you need to, if you're not kind of feeling a little chill, like, oh man, that's cool, then you're misunderstanding this. What just happened to those 2 points right there that were 0.01 apart? What happened to the 2 points? They just touched. You understand that? Like we were able to let x actually be 3. We weren't able to let it be 3 here. We couldn't do it. But over here, we were, which means the 2 points just touched, which means our slope is actually perfect. Like it didn't break. Turns out this will happen every time with calculus. You'll always be able to put 3 in.
So is that the instantaneous rate of change?
Exactly. Yep.
Okay.
That's the slope at that point, or to put it in English, that's the instantaneous rate of change. Back here, we were getting average rates of change. Between 3.1 and 3, 2.1 was the average rate of change. Between 3.01 and 3, 2.01 was the average. You have to average it because you have 2 separate points. Between 2.9 and 3, the average rate of change was 1.9, or slope, the average slope. This isn't a practical application, so you would typically not use the words average rate of change. If this modeled, you know, the price of a house or something, then the words average rate of change make more sense. But down here, it's not an average anymore because the 2 points are exactly the same point. It's now instantaneous. It's perfect. The 2 points are the same point. It's just weird. It's like it shouldn't work, but it does. That's kind of the amazing thing. And so now we can actually say with confidence, the slope is actually 2. It's perfectly 2. It's not 2 and 1/967th. So amazing. That's really cool. And this is not hard, thanks to the fact that factoring is a skill that we have, right? But remember, this is working with the easiest equation we have. We still have to do this with natural log and square roots and all kinds of nasty business later on. So what I just showed you, I'm not going to show you till 2.3. Well, yeah, again, I just did it. So, but you're seeing the big picture. That's what I need. I need you to see the big picture, because the problem is this is what your assignment today is going to look like. This is the question you're going to get today. You're going to be asked for sine of x over x or something like that. Now notice that's still a fraction, so does it make sense that came from slope? But this time we didn't draw the equation and, you know, say what's the slope at a particular point. It's just there it is sitting there, right? The book is just going to give you problems and say here's something, and I'd like you to figure out what the limit of this is at, well, here's something they're not going to ask, as x approaches 2. Why are they not going to ask that? Why does that never happen in calculus? Well, is there any reason you can't just put 2 in there? Like why should you start with 2.2 and 2.1 and 2.01, or maybe 1.9 and 1.99? Can you do that? Sure. But notice in this case, there's no reason you can't just put 2 in there. It doesn't blow up. Do you understand that? It's sine of 2 over 2. My calculator says sine of 2 divided by 2. It says it's 0.45, and it's a weird decimal, so I in a sense don't have to. I don't have any choice but to say approximate, but it's like that. There's no reason I can just plug that in, and so you won't be asked that question, and that never happens with calculus. What does happen with calculus is the same exact expression, and this is actually, you don't know it, but this is kind of a famous little problem, and this is the kind of thing only a mathematician invents. They're going to ask this question when x approaches 0. What happens to that expression when x approaches 0? Well, the sine of 0 over 0, that ends up, do you know what the sine of 0 is? You should know that in your head. You should not need to get your calculator out. Let's just quickly refresh that. Let's see. I'm on the unit circle, 0 degrees or 0 radians puts me right there. And what is the sine of that? What do I need to know about that point? What does the sine of that point tell me?
It's 0, right?
Yeah.
It's opposite.
Yeah, it's the y coordinate of that point. And the y coordinate of that point is 0. So this becomes 0 over 0, and like poof, it explodes, right? So now you don't have a choice. And this is what 2.2's assignment looks like. You don't have a choice but to say, well, I can't put 2 in. Just like back here, we couldn't put 3 in, but we can put in stuff close to 3 and see if it still approaches something. But this is not like that expression there. Like, you can't factor this. There's nothing you can do to the sine of x over x. You can't like factor it or like change it. You're not ever going to be able to put 0 into this. Do you understand that? That's going to happen sometimes in calculus. But you don't need calculus for calculus. Just start plugging stuff in that's close. So again, I'm going to do what I did before and say x, and I'm going to pick stuff close to 0, like 0.1 and 0.01. Those are really close to 0. And so, and this time, I mean, I guess I'll still use the word slope, but really it's not, this didn't come from a slope. It's some expression that some nerd gave me to plug in, right? So let's see, when I say sine of 0.1 divided by 0.1, I got, did you get 0.998? That's what I got, approximately. You got to be in radian mode for that. And by the way, there's nothing in this problem saying you're in radian mode. I'm just telling you now, maybe for the first time. And then I'm going to go back and try it again with sine of 0.01 divided by 0.01. And this time I got 0.9999. So what's your hypothesis? What does it look like? What does it look like the limit of sine of the expression sine of x over x is as x gets really close to nothing? What does it look like that's approaching?
1.
Looks like 1. Now, to check this, we might also want to go on the other side of 1. In other words, I'm sorry, on the other side of 0. In other words, like, what about negative 0.1? Like, go on the other side, just like 3. We went on the high side of 3, 3.1. We went on the low side of 3, like 2.9. So what about negative? Like, I'm going to type that in. What's the sine of negative 0.1 divided by negative 0.1? Good news. It's also 0.998. And so I'm sort of ready to be done now. I'm ready to say I'm pretty confident it's actually 1. Do you agree with that? Now again, can we be sure? Is there any reason it couldn't be 1 and 17 5/millionths or some ridiculous fraction? No, there's no reason for that. So I'm ready to bet that this is true, but I definitely don't have a guarantee. Do you see the difference? Like, again, that's, are you a mathematician or just a practical person? It's the same discussion.
I was kind of thinking a little bit about what you were saying a moment ago about, like, up in the blue, where you were writing about the whole how we were able to put 3 into it after mixing it around, and I feel like there was something about that didn't really work for me. I don't want to hold things up if you're moving along, but I feel like up in the blue section, when you canceled out the x minus 3's, would that really work? Because I feel like the assumption is that any number divided by itself is going to be 1, although that's usually true unless both of them are 0, because then you're dividing by 0. So the assumption is that x is not 3 in either one of those. And so
it's kind of bothering you that we took that away, because in a sense 3 was a prohibition, right? And so if I cancel those out, the prohibition still exists, and so that's bugging you a little bit. And I agree. The simple answer, for the sake of And we can talk after class more about this if you want. But the simple answer is it is okay. Like it allows us to do what we needed to do with this, which is we wanted to plug 3 in, and since they canceled out, we plugged it in and it produced the answer. But you're right. What's bothering you is, can the 2 points touch? No. Like if the 2 points, if I have 2 points, does it make sense there's a line that defines them? But if they could become the same point, does it make sense there's nothing saying what direction it goes anymore? I mean, that's kind of what's bothering you in a sense. So again, you're right to be bothered by that. And this is why ultimately the mathematics gets hard if you really want to question things. Like there's the devil's in the details, if you will. The proof that that's okay to do, you know, is this kind of a thing. And it's not the first time that logic is gonna happen in here. And the simple answer is yes, it's okay to do here. The slope really is too, and that really does work. But the fact that you're bothered is also good. I guess I'll just leave it at that for now. I want to introduce you to a little bit of language that you're going to see in this section, which is this. Do you agree here we chose something on the high side of 0? Like back here, we chose something on the high side of 3. There's a symbol for that I want you to be aware of, and it's kind of a good one. It's kind of a good idea. In other words, this is 3 with a little tiny plus sign up there where you put an exponent. It's not on the other side of 3 because then it would look like positive 3, right? And that just looks like a positive sign. But if you put it over on the other side and not just to the right of 3, but up high, that's a symbol that mathematicians have invented to say what we just did there. Like pick something on the high side of 3. If that's true, what would you call this over here?
Approaching from the negative direction.
From the negative side, from the low side. I like to think of that as high side and low side. The plus is the high side of that number. So the negative does not mean negative number. Does that make sense? That's what's kind of hard about this. And so down in this problem, in a sense, this was the high side of 0. And what we did over here was the low side of 0. So if you want to kind of be sure that your slope is right, like you kind of need to do both just to kind of be sure. I mean, that's kind of the idea here. So let's see, let's just do kind of another sort of a book related kind of a question. What's the limit of this statement? This is a really good problem, by the way. It's good because I worked really hard to make it right before class, and I'm really happy with it. And you'll see why in just a second. So again, here's a fraction. This came from a slope, but we aren't worried about that right now. And so the end result is we'd like to plug a number into this. And unfortunately, the one number we end up wanting to plug in is the one we can't plug in. But that's, again, what your problems in your assignment today are going to look like this. What's the limit of that expression? What's the limit of that, which is a slope of something, as x gets really close to 1? Now, what happens every time is, what happens when you try to put 1 into this? If you put 1 into that, you get 1 plus 2 minus 3 on the top, which is 0. And on the bottom, you get 1 plus 5 minus 6, which is also 0. You get 0 over 0. This happens every time when you're doing this in calculus. You end up with like, oh, dang, I can't plug in 1. But there's no reason you can't plug in something close to 1, right? Vale, you had a question or comment?
Yeah, can't we do the same factoring trick? Because I noticed that it factors out to x plus 3 and x minus 1 on the top and x plus 6 and x minus 1 on the bottom.
Yeah. Now, in this case, because again, this is a fairly simple problem, we will be able to do the same factoring trick. But in your assignment, just like in this problem, you don't always. I can make up problems where you can't. So just to slow down a little bit, and we'll get to that, you're exactly right. The 2.3 version of this is factor it, and then just tell me the correct answer. You know it's perfect, and you're done. The 2.2 method is, well, we don't know how to do that yet. And there are problems that you can't do this to, and I'll give you another one in a second where you can't do that. You don't have to do calculus to do calculus. Just pick stuff close to 1. So again, let's do the same thing. Let's say there's our x, and this time instead of calling it a slope, I'm just going to say it's an equation. And so first let's pick stuff on the high side of 1, like 1.1 and 1.01. And again, I'm going to remind you that that's like 1 plus. That's the high side of 1. So let's pretend we can't and plug this mess in. This is pretty time consuming to type all this stuff in, right? I'd like you to think about, is there some way you could do this that would maybe save you some time? You should be sophisticated enough to come up with a method, but it's like, God, that's a lot to type in. And I'm going to do this 4 times because I also want to try 0.9 and 0.99. In other words, stuff that's on the low side of 1. I'm going to have to do this 4 times. God, that's tedious. There's some better way to do this. Mathematicians are lazy. When I put 1.1 in, I got something rather disappointing. I got 0.577. In other words, all the previous problems, like I immediately thought I recognized the answer, but I don't know about you, but I look at 577 and think, oh, that's a weird place to land. That isn't landing on some nice whole number. Maybe it's 0.6. Maybe it is going to some nice whole number. Well, I'm going to try 1.01. And although that is really close to 1, I still got an unsatisfying number, and it's certainly not on its way to 0.6 now. I was kind of hoping it was going to be 0.6, although that's a bit of a weird decimal. At least it's nice. Well, that's not very satisfying. And then when I went in and tried 0.9, I got 0.565. And 0.99, I got 0.5708. I'll call it 0.571. Would you agree we're like landing out in the weeds here? But from a number perspective, we're not. Like, math doesn't care. This isn't out in the weeds. It's an answer. So just to show you something in a sense I want to say I think you should know, I just cheated to do this. I'm too lazy to type all this stuff in, and I got a machine here that I should be using. So what did I do? I went to the y equals screen and I typed that expression in, and then I hit graph and I got this graph. You know how to do this, right? I got this graph, and then I hit trace, which allows me to cruise along the graph. So now it's like cruising along the graph, and I typed in 0.99. I know you can't really see this, but at least you're getting an idea here. And I hit enter, and that's where I got my 0.5708 number. Like typing stuff into equations and so forth. And remember, keep in mind, like, how does somebody like Archimedes that I introduced you to, one of the famous mathematicians, or maybe Euler, we've talked about those two guys. What about Euler? How did they do this? Well, they got out their rock and started scratching it on the ground. Does that make sense? I mean, they barely have paper, you know, a quill and some ink, and they certainly can't plug in 1.1 as blithely as you and I do. And even then, I'm sitting here saying I'm too lazy to even type it in. Like, I even found even a faster way, right? But our ability to play with this is just so cool relative to the people that actually discovered this stuff. Like, they had to work their mind a lot harder to get answers like this. Can you appreciate, like, could you do this without a calculator? Just ask you that. Could you even do it? Can you square 1.1 and then add 2 times 1.1 and then minus 3? You get a decimal there. And then on the bottom, 1.1 squared plus 5 times 1.1 minus 6. Now you get a decimal. You got 2 decimals to divide. Can you still divide decimals and ugly decimals at that and actually produce 5.77? I mean, I think I could, but it's definitely going to take me, I don't know, 10 minutes per trial, if you will. And that's because I have paper, right? Could you do it in your front yard? Like, don't take for granted the time in which you were born and the country in which you were born and your ability to play with this. In the generations in which this was discovered, they actually needed calculus to get the answer to this question. But as I said, we don't really, because we have such amazing technology that we can get really close to this answer without actually having to really do anything other than just kind of play around. Well, speaking of lazy, I'm going to copy that expression down here. What would you hypothesize then the answer to this is? And if you have tried factoring it, like Vale mentioned, like I don't want to hear the best answer, but based on what we have so far, what would you say our answer to this is? Would you agree that the best we can do is, well, 1.01 was pretty close and 0.99 was pretty close. Like, aren't those kind of the same answer approximately? And so in a sense, I find myself feeling like I need to take that equal sign away and say, well, I guess it's maybe approximately, I guess maybe I could say, well, it's halfway between those two, like 0.5715 or something like that. But it probably isn't that, but at least that's close. Do you see what I'm saying? But notice how it isn't like all satisfyingly landing on some whole number like 2 this time. Now, this actually has an exact answer still. It's just that you don't recognize the answer to it. Now, from what we've been playing around with lately, does it make sense? It could be something like pi squared over 4, or it could be like e divided by 6, or it could be some weird expression that we don't recognize really easily. But the problem is this just isn't a very satisfying decimal. And as it turns out, this is the decimal that never ends. And so you kind of can't answer this question well unless we use the concepts of 2.3. So let's take a second and factor this. Again, this turns out to be, because I've made this to be nice and easy, this turns out to be factorable. In other words, doesn't the top factor to x plus 3x minus 1? And doesn't the bottom factor to x minus 6? x plus 6, x minus 1. Why is that particularly wonderful that it factors to that?
Because the x minus 1s cancel out.
Yeah, it's not just that it simplifies. Remember, what we were really trying to do here is we were trying to let x equal 1. It's not just that it simplifies, it's the fact that that simplification now allows you to actually put 1 in. Does that make sense? The prohibition against plugging 1 in has just been lifted. You realize how cool that is? And so now x can actually be equal to 1. And what does that equal if you put 1 in? Somebody say it. I know it's obvious, but
4 over 7.
4 over 7. So the only problem is you and I are too dumb to recognize 0.571. You don't recognize that decimal. Does that make sense? I didn't. You didn't look at it and go, oh, isn't that 4/7? Like, I don't think there's anybody in here who did that. If there is, like, I'm really impressed with you. Now, had it been 0.3333, I would have said, I recognize that one. That one is 1/3. Like, wouldn't you have probably thought that? Or what if it had been 0.5? You go, oh, that's 1/2. Or 0.75, oh, that's 3/4. Like, there are some I recognize. 0.1111, that's 1/9. There's some I recognize, but I don't recognize 0.571. Now, did you do that on your calculator? What's 4 divided by 7? Like, sure enough, it's 0.571428. Like, yeah, that actually is working, isn't it? And so do you agree that 4/7 is a better answer because it's more perfect, and we don't have to sit there, all lame and like plug points in and make guesses? Like, that's cool to be able to, get it perfect and not have to sit there like an idiot plugging numbers in and just kind of guessing, right? I mean, that's kind of cool. But you do need to understand the difference between those two requires a lot of knowledge. Like, even here, you have to have the ability to factor squared equations. And you did sit through a lot of classes before this to be able to do that boring skill. Here we're able to kind of use it for something, which is kind of cool. The problem is that technique just gets harder. Like, that the ability to do this just kind of gets worse. So again, what's beautiful is we just sort of let the second point be x is 1, and now we actually have a perfect slope, which is really kind of cool. So here's a problem where you're going to have less success with this. Let's see what you do with this beauty. You're not going to be able to do the algebra for this one. Let's try this example out. What is the limit of, let's see, I want to make something up here that's kind of fun. What shall it be? I think I'll go with x minus, I don't know, let's go with 16 over the square root of x minus 4. There's a weird fractional expression. And notice it's already uglier, right? Because it's like got a square root in it. Remember, square roots are kind of terrifying. Remember simplifying those? Remember simplifying ridiculous square root expressions in algebra 2? It's like, oh God, horrible stuff. What do you suppose I'm going to ask you to let x get really close to here?
0.
2.
Not 0, because if it was 0, it's a good guess, Bill. If it was 0, there's no reason you can't put 0 in. You understand that? If you put 0 into that, you get negative 16 over negative 4, which is 4. So if I did ask that question, you'd say, hey, great. I don't have to, I can just put 0 in, and I got the answer is 4.
16.
If I did ask
16.
that, 4.
16.
16 is the one thing that you don't want me to say. And again, unfortunately, when we do this for real with weird functions, the one thing that you can't plug in is the one thing we're going to need to plug in. You just saw that happen a second ago with the parabola. Yeah, it's 16. And so if you put 16 in, you get 0 over 0. And so you have no choice here but to do what we've been doing, which is to stick something in close to 16. And then you'll still be able to guess. And this time you will get a recognizable decimal. Like you're going to get something, you're going to go, oh yeah, I see. I'm pretty sure this is it. It isn't going to land in such a weird decimal. So 2.2 is just guess. Guess close. So let's see. This time I'm going to say I'm going to choose X, and I'm going to choose, I don't know, 16.1. Well, maybe you're tired of wasting your time. Why even try 16.1? Why not just try 16.001? Like, do you really get really close? Probably this is good enough to just get, we're done. Like, just try one thing and you probably can already estimate the answer. And then this time I'm going to write the word expression, in other words, you know, whatever fractions. Like, what do I get when I put 16.001 in? So I'm just going to type it in this time, 16.001 minus 16 on the top, divided by the square root of 16.001 minus 4. When I did that, I got 8.000125. And so I'm already ready to say, I'm already ready, if you will, to conjecture the answer to this is 8. Do you agree with that? I'm not really sure, but I'm ready to conjecture that. Educated guess. And again, it's only because it happened to land so close to a nice number, and you know, math being what it is, math books being what they are, it's like probably is 8. But just to be sure, I'm going to go try, you know, like 15.999, like something on the low side of 16. So I'm going to hit second entry and retype that, because this time I just typed it all in. Since I decided not to find many answers, I just was going to find a few. So 15.999. When I typed that in, I got 7.9998. So okay, now I'm really sure. Does that make sense? I'm ready to place your bets. However, as we've been saying, is there any reason 8 isn't some magic number? Like, is there any reason that it actually has to be perfectly 8? Could it be 8 and 1/900th or something? It certainly could. So we haven't proven this by any means. But again, if we're trying to build a shed outside of our house and we're doing math like this, 8 will be close enough. Even if it isn't 8, it's darn close, right? I mean, look how accurate these numbers are. Those are really close to 8, right? So close enough for anybody. I've never met anybody for whom this wasn't close enough. It's close enough to build a bridge. It's probably close enough to launch a rocket to the moon. I mean, if I'm doing this as a part of something like that, how fast is my rocket going? About 8, probably is going to be okay, right? That's all you're going to see in your assignment tonight. Somebody in 8 o'clock class asked, is there, any way to like do something to that? So the prohibition against plugging in 16 is lifted, and then you can actually plug 16 in and kind of get exactly 8 as the answer and kind of prove it. The answer is yes, it's just not near as obvious. And I doubt that you are sophisticated enough or practiced algebra enough that you could come up with a good idea as to what you could do to that. It doesn't just factor, right? It's kind of like sine of x over x. Like, what am I going to do to that to be able to put 0 in? What am I going to be able to do to this to put 16 into this? And it's like, that's not super straightforward, but there is actually a way here.
Wouldn't you start by considering square root of x to be x to the 1/2 instead, or to the -1/2, so you can have it on top?
Yeah, so you're starting to experiment, Vale, with like, first of all, I look at square root and I think, oh, I hate square roots, and I really do. Like, I hate fractions too. I'm thinking, like, could I square that somehow? Or, like Vale's saying, thinking of the x to the 1/2, is there, maybe I could square it in some way and get rid of that, and then it would look like a squared equation, and then maybe I could factor it. And so, yeah, I mean, and just as a little side note, in my world, I find myself thinking, let's see, could I spend 4 hours on this, like trying to come up with a way on my own, which actually seems interesting, doesn't it? Like, to a point. But then I think, God, it's a nice day out there, and I got a mountain bike sitting in my garage, and like, I think I'd rather go mountain biking. Or, I worked on it for 10 minutes, but then it's like, wow, Netflix, it's really kind of fun. We have a lot of fun options in front of us in our culture. But again, put yourself back in somebody in the year 600. They didn't have Netflix, they didn't have mountain bikes. A lot of math got invented by people that kind of got interested in what I hope you agree is kind of an interesting question. Like, is there some way to do this? And remember, if you don't know the answer to that, the actual answer could be no. Like, you could spend 2 years trying to do this, and you've tried 2 years and you never find a way. And then you actually turn your attention to maybe proving that it's impossible so that you can quit. Like, this is what mathematicians used to do. Little side question that just occurs to me really quick. I'm going to erase this, but this is something mathematicians got interested in. Is there's an angle. Now, do you agree I drew it randomly? Therefore, it isn't, like, I could measure it with a protractor, and if that came out 36 degrees, it still isn't 36 degrees. It's 36.125987. Like, it's a really weird random decimal angle. And they asked the question, is there a way to cut that angle in half without even knowing what it is? And the answer is yes. If you measured a distance away, I measure that distance with a compass, even like I could use a stick and measure that distance. And then I measure that distance again on the other side. And then I took off out into space between these two, and I measured the same distance and the same distance. Then that angle, that just cut that angle in half. Even if that was 36.132965, I just perfectly, theoretically cut that angle perfectly in half. Do you understand that? Now, of course, you might be thinking, like, who cares? Who would want to do that? I agree. But if you don't have Netflix and mountain bikes, maybe that suddenly gets interesting to you. Or if you're a true mathematician, maybe it's like, those are just interesting questions that you could ask. So somebody then asked the question, is there a way to cut that angle into 3 equal parts? That's an interesting question, isn't it? At least a little bit. And guess how long people tried to come up with a cool way to do that? I shouldn't have said guess, because I don't know the answer. Years people tried to come up with the answer. And then mathematicians turned their attention after many people slammed their brains against this, many smart people, which is a really simple question, isn't it? Isn't it a simple question? They turned their attention to trying to prove that somehow that'd be impossible so that they could quit looking. And that's really cool to think about, because it's like, I don't know, if 10 smart people spend 3 years on it and nobody finds it, does that just mean nobody's tried a cool creative approach to it? They actually proved that it was impossible, and then were able to quit. Now, I hope that bothers some of you. I hope some of you are like, oh yeah, I just think they haven't found the way yet. I don't know how they proved it. I haven't looked into that because I have a mountain bike and I went mountain biking instead of answering that question. But that's kind of what I mean. And so, I mean, this is what mathematicians do, though. I guess I just want you to understand. They ask questions that are interesting to them. If it's interesting to nobody else in the world, does that matter? No. If it's interesting to you, it's play with the mind. I mean, I like playing with my mountain bike. That's like playing with your body. But I like playing with your mind, asking interesting questions and trying to find the answer to them. It's really cool. That's how we ended up with most of the math we have. Occasionally, what people discover is kind of cool. Like, for instance, somebody said, is there a way to solve squared equations? And so ultimately somebody invents the quadratic formula. Now we use that in physics to launch rockets and stuff. We use it. It's kind of cool. But a lot of math that was discovered is just interesting, but nobody's sort of found a use for it yet. Again, I'm the type of person that if you find a use for it, I'm a lot more interested than if it's just theoretically beautiful, although I see the beauty of both. So perhaps after class, if you're interested, I'll show you this, but that's kind of that's the topic of 2.3 is like, is there some way that I could manipulate that? And in this case, there actually is. 2.2, you're done. Hey, it looks like 8. Good enough, we're done. So the idea of just the idea that, we're close enough to guess 8. Interesting. Let's see, what time is it? Let me ask you, let me just give you another kind of a historical thing. If you're this far in math, you should have heard this before. Now, you probably haven't heard this before, but because you took this math class, you should. Have any of you ever heard of Zeno's paradox? If you have, then you're a lot more well-read than I am. Like, this is something you should have heard of in calculus, but not until calculus. Here's Zeno's paradox, and I'll ask it to you now. I'm sitting in this room, and here's a wall, and I'm standing over here. And I'm going to go to that wall over there. But I'm going to get to that wall in a kind of an unusual way. Rather than just walking over there, I'm going to kind of jump to the wall by cutting my distance in half. So however far away I am, I'm just going to kind of go, thunk, and jump there. And then I'm going to cut that distance in half and jump there again. I'm going to cut that distance in half and jump there again. The question is, in Zeno's paradox, you could tell Zeno was a Greek person that didn't have Netflix and mountain bikes, because that's a really weird question to ask, isn't it? And yet it kind of captivated the Greeks. The question is, does he make it to the wall? Jesse immediately weighs in with a no. This is why I like to see your faces, by the way, if you're willing to show up, because it's just, I don't know, like other people just saw you go, I don't think so. And now others of you are going like, oh, she thinks no, I wonder what I think.
What if he just kept going faster?
Well, it's
he went twice as fast with each jump.
Yeah, okay. So you make that move every billionth of a second. You're super quick. Now, if I said each move was made like 1 year apart, like, man, that guy's got nothing to do. That's very different. But actually, the time doesn't make any difference. The paradox remains the same, which is, does he get there?
Suggesting, because the distance is getting it's getting cut in half each time.
Yeah.
But what if he moved twice as fast with each jump also?
Still doesn't really change anything, in the sense that the question is there always still distance between him and the wall? If there is, then he doesn't get there.
He'd be moving infinitely fast.
Of like, is there infinity?
Isn't it funny? Like, some of you are like, it's got me. Like, this is an interesting question.
So we can set this up as a series, right? 1/2 plus 1/4 plus 1/8. And then we find the limit as x approaches 1, right?
You sound like you've taken Calc 3 before by what you just said, Vail, because that's the subject of Calculus 3, which is kind of an infinite series. In other words, 1/2 plus 1/4 plus everybody understand what he's saying? 1/2 plus 1/4 plus 1/8. Math, and that's kind of what mathematicians do, is they try to take this away from a picture and sort of write it down mathematically and then try to, attack it with numbers. They try to attach numbers to things. And that's what's so cool about math, because there's a guy that wrote an essay a long time ago named Eugene, I think it's Wigner, Vignoir. And his paper was titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." In other words, it's just so weird that somebody like, from yesterday shoots an arrow and then they start wondering things like, where will it land? How high will it go? Like questions a person might ask. And then mathematicians come up with a way to numeratize, that's not even a word, but throw numbers at that problem, and then they do math on it, and then they can actually come up with something that's like ridiculous. They actually can predict based on where that thing's going to land and so forth. And so it's just weird that we live in a a world that has trees and gravity and so forth, and yet somebody would be able to invent this non-tangible subject called math that most people hate because it's not tangible, and I get that, that actually gives you the ability to come up with an answer to that question. And so you're right, Vale, like turning that into taking the picture away and saying 1/2 plus 1/4 plus 1/8 plus 1/16, and you never quit. Isn't that what we did? Isn't that exactly what we did yesterday with 1/1 squared plus 1/2 squared? And like you were able to turn that into that, which shows some strength of mind, Vale. So I compliment you on that. And basically the answer to this question has to do with infinity. The answer is no, he doesn't reach there if he stops. If he gets tired of this game and says, I stop. Because won't there always be distance? Yes, there'll always be distance between you and the wall. Now it'll be microscopically small. And it's hard for you to imagine this as a person, because it's like, I got a pretty big nose, so my nose will hit the wall, right? But you're thinking of this as a point. You're a point. And if you cut the distance in half, there's always distance there. It's never gone. And so you'll get as close as you want, and you'll get pretty close pretty fast. You notice that? You get ridiculously close really quickly here. Even if you go slow, you get there really quickly. But there's always distance, and you actually don't get there. Well, unless you make infinitely many jumps. If you make infinitely many jumps, then you actually do get there. So it gets at the concept of infinity. What have we been doing? We get infinitely close to 16 here, right? If you get infinitely close, then the answer is 8. But you can't actually let x be 16, and so it's like you can't do it. You can't make infinitely many jumps. Infinity is not a number. So, our minds explode with this. Let me give you another quick, I'll save that for later because we're running out of time. I need to show you one other thing that is in your assignment that I kind of don't want to show you, because in my opinion, what we've been having is kind of an interesting, cool discussion about infinity. And now I'm going to show you how to get a couple questions right in your assignment. And this is just such a contrived, kind of a stupid problem. And this is part of the reason I'm skipping so much of chapter 2, because of things like this. But I just feel I feel uncomfortable skipping this, I guess, just in case you leave my class and go to somebody else's. But I just want to I want to give you a shot at thinking maybe a little more mathematically about this question. I'm stealing a question straight out of your book here. Isn't technology amazing? Like I took a picture with my phone and I loaded it in here. Oh my God, it's incredible. We're going to try to do what we just did, but we're going to do it with a graph. Like when I say what we just did is like, didn't we get our answers here by plugging 16.01 into that equation right there, and then out popped our y value? Like this was our x and this was our y, right? We popped out. It's just that this time we're going to get our y from a graph. And this graph, however, is a really weird, contrived, utterly stupid graph. And I choose my words carefully when I say that. Let me show what I mean. Well, it's all broken up, right? Like if you graph an equation in your calculator, don't you get kind of a smooth connected curve? You don't get like jumbly chunks of curves. So this is mathematicians just making up something weird, but I do this because I want you to understand the concept of a limit. So let's stare at, well, let's stare at question B first. First of all, can you decode that language right there now from what I showed you today? What is the limit of f of x? In other words, what is y? What is y as x gets really close to what? What does that say? X gets really close to what? Not 1, but what?
Is that -1?
not negative because it's not in front of the one.
Isn't it like
It's really
0.99 or something?
Yeah, it's approaching 1 from the low side. In other words, we're not choosing x to be 1, we're choosing 0.9, like something on the low side. So x is 0.9, x is 0.99. Okay, well, we don't actually have an equation to plug that number in. We have this graph over here. We'll take a look on the graph. If you let x get close to 1 from the low side, aren't you creeping up to 1 like that? All right. And so where am I on the graph if I do that? Oh, I'm up here. I'm creeping up. Well, what am I getting close to? What y value is that working its way toward?
2.
2. It's working its way to 2. So if I'd plug this into to some equation, I would just see it getting close to 2. I mean, isn't that what we were just doing a second ago? We plugged 16.01 and we said, hey, look, it's getting close to 8, right? Isn't that right? That's the same thing. It's no different. Don't freak out. This is easy. So it looks like it's getting close to 2. Well, what about this second question? What's this saying? This is saying let's also choose 1, but this time what are we doing?
Towards 3.
Closer. So I like to think of this as, the low side of 1, whereas this says 1 plus, so this is the high side of 1.
So would this be 1.001?
Yeah, 1.001. So down here, this time I'll change colors just because I can. This time I'm getting close to 1 by choosing stuff on the high side of 1, which puts me over here on the graph, right? But notice I'm still going to the same place. I'm still going to 2. You see that? Both places I'm getting close to 2. So this answer is actually the same. This is still 2. Yet, what's the answer to this question? This is actually saying x is 1. If you look at the graph and you put in x is 1, what does it actually say the answer is? I mean, it says, yeah, there's a hole in the graph down here, and they're just saying like, surprise, it's somewhere else. Does that make sense? Now that never happens in calculus. It's not just like surprise, it's something else. So the actual answer to the limit or when x is 1 is actually 3. But if you're to get really close from both sides, it's actually on its way to 2. What's this question asking? Notice there's no little plus or minus to it. This is not obvious at all. What's the limit of f of x? In other words, what is y as x is close to 1?
Isn't the answer for this one either does not exist or undefined? I forget which one. Because there's a hole there.
Notice this is a little bit confusing. But the difference here is that A and D are almost the same question. It's kind of like x is 1. You see what I'm saying? But in A, x actually is 1, whereas in D, x is close to 1, but it isn't 1. You understand that? It's working its way infinitely close to 1, like the dude walking toward the wall. He's trying to get infinitely close to the wall. Well, because of the graph and because of this limit nonsense, if you get really close to 1 but you don't get to 1, both of these agree that it's 2. Therefore, the answer to this is 2.
So you're going based on the evidence of the other 2 questions?
Yeah, because the reality of what we did today really kind of it's the same thing. It just didn't have that point in it, right? It's not like surprise, it's somewhere else. What we did today is let it get really close. And I just need you to understand that that's exactly what we did right here. We saw ourselves really getting close to 8 from both directions, so we said it's 8. But the cool thing about, math and calculus is it's never going to be like, surprise, it's 9, you got it wrong. Does that make sense? It looks like 8, it's 8. Like, this isn't complicated. However, something very different happens over here in this contrived example. If we start looking at 3, we looked at x as 1. If we start looking at x as 3, it gets weirder. So let's look at the questions, like right here. Here's one of them. What's the y value? I'm looking at this one, f. What's the, again, it says limit of f of x, but it's like, that's not that complicated. It's just, what is y as x gets really close to 3? But from which side of 3?
The low side?
the low side of 3. So then I go down to the graph and I say, okay, I got it. I'm approaching 3 from the low side. But now go look at the graph. Where are you on the graph? Notice there's like 2 separate graphs. Well, I'm over here. I'm actually working my way up to that. So what y value am I at? Notice you say I can't tell because you took the screen away, right? What are we getting close to?
4.
We're getting close to 4. So if you approach x is 3 from the low side of 3, then you're getting y values that are getting closer and closer and closer to 4. So that's the sort of technical answer to this question. It's 4. You're working your way to 4. You're not getting 4. You can't get 4, just like we couldn't get 8 a minute ago, but it looks like 4. I'm ready to sort of guess it's 4. However, something really weird happens when you, where did this go? There it is. G. What if you approach from the high side of 3?
Going towards 2.
Yeah, over here from the high side of 3, notice because this is a broken graph. In other words, it's broken into 2 pieces. Mathematicians say that's not continuous. It's not a continuous function. One of the reasons I'm telling you this is for a lot of the rest of this class, you're going to see something like f of x is a continuous function. And they'll say that and you're like, why are you even telling me that? Well, they're just sort of saying it's not broken. If you had a broken graph, which you never have, like you have to make one, you have to contrive it. This doesn't happen with real problems. But if you approach from the high side of 3, notice you're on a totally separate graph. You're over here. And what y value are you working your way to? One of you said this already, I know, but notice it seems like you're working your way to a y value of 1. Like you got a totally different answer. You're not getting the same exact answer here. Do you see what I'm saying?
So if we were to assume the average, what would you put?
Yeah, that's a good question. And basically this doesn't work. Like you can't answer it. And for that reason, what's the answer to this question? Then what is the limit? What is the y value of x gets close to 3, considering it tries to be 4 on one side and tries to be 1 on the other? You don't take the average, you say no such animal. Like that's a symbol for nothing. Like there isn't an answer to this. Like you're getting, this is weird. Like you're again, this won't happen in calculus because when you look at an equation, it's always smooth and connected. There's not some break in it. Does that make sense? But this is kind of cool to just think about from a theoretical perspective. Yet, what's the answer to f of 3? Like, can x be 3? Well, again, notice they just kind of, oh yeah, I'll just stick an answer in there somewhere. Like it's 2. You see what I'm saying? There isn't actually an answer to, with x is 3, they're telling me there's a dot there. So really, do you understand this is like 1, 2, 3, 4, 5 graphs. This is like 5 separate graphs in a sense. So really kind of contrived stuff. Let me show you something on Desmos from a problem we did previously that I have now. Let's see, I gotta make sure I do the right one. I'm gonna go all the way back to the start of this class where that was it. X squared minus 4x plus 3 over x minus 3. We were playing around with that. And at the time we were trying to figure out, what happens when you get really close to 3, right? And we played around with numbers that got us really close to 3, right? I'm sorry, it was 2. Wait, yeah, 3. Right here, right? We're picking numbers close to 3, right? And so what if I made a graph out of that? I'm going to go make a graph out of x squared minus 4x plus 3 over x minus 3. I'm going to graph that in Desmos. Oops, that's not what I want. Delete. In order to get this to type into Desmos or your calculator, you can do this on your graphing calculator too. As a matter of fact, I'd encourage you to do this on your graphing calculator with me. I'll show it to you in Desmos and you show it and you do it on your calculator. Dang, I wish I had a good memory. What was it? X squared minus 4x plus 3. Divide. And notice I have to have parentheses to get this to work. Does anybody have a good memory? Was that the problem?
Correct.
It was? Oh, thank God. And now, because it looks stupid, I'm going to go back and get rid of those parentheses. And so, like, look at that graph it just made. That's weird. It made a straight line. Isn't that weird? Does your graphing calculator do the same thing? Should look just like mine. And because I'm lazy, I'm going to go back and change y to f of x so that I can use it. I can use that function notation to do some work for me. Because what I'd like to do is plug 3 in. So I want to say, what's f of 3? What does the, what does it say? And what does your calculator say when you do that? So you type this in, you hit trace, and then you type x is 3. What does it say y is equal to? Somebody say this.
An error.
Yeah, it says error perhaps. What do some of the others of yours say? That's not all it says. If you hit trace,
Undefined.
3. Does it say something? It actually says undefined? I thought it just, like if you look down where it says y, if you type y equals this expression, I thought when you looked at y, it just said nothing, like there's just nothing. There's nothing there. Now, the reason you shouldn't be surprised it looks that way is because we saw that that factored and simplified. What did it simplify to? Well, wasn't it like x plus, I forgot, x plus 2, I don't know, I forgot what it was. As I said, I don't have good memory. I'm going to take this back to the, I'm almost done. I'm going to shut up here in a second. I see the time. So you don't notice it, I guess, at first inspection, but given the fact that, as you know, it doesn't let you plug this in, what it means is there's a, go away. There's actually a microscopic hole in that graph. Notice there's no circle sitting there. Mathematicians add those to say there's a hole there, but there's actually a little hole in that. Now, if you zoom in, will you see it? The answer is no, kind of like because of Zeno's paradox. How big is that hole? Well, if it was like 1/1 billionth of a micron, you'd never see it. Does that make sense? I mean, what does it mean to be a hole? There's a hole in the graph. Is it okay for x to be 3.000000001? Yeah. So that's a one heck of a tiny hole. So it's not like if you graph something, you're going to see the hole. Do you see what I'm saying? That's why the graph, that's why it's teaching, that's why this problem exists, or why the last problem I gave you exists. The problem is there really is a hole here, which is why when you plug 3 in, you don't get the right answer. Yet, can you see, and I'll finish with this. Oops, that's not the right thing. Oh, I can't do that anymore. Does it make sense that from the high side of this, I'm getting a y value of 2, and from the low side of this, I'm getting a value of 2? So it's perfectly okay to say that the limit of this fraction is 2 as x gets really close to 3, because it's getting close to 2 on both sides. My point is that's what we've been doing. It's just that, and this is getting at what Felix answered earlier, or asked earlier, which is kind of the theoretical side of this. And mathematicians run down those roads to kind of prove that this is all okay. This approaches 2 from both sides, so the limit of this really is 2. And notice that 3 says as x approaches 3, there's no distinction between 3 positive and 3 negative. In other words, I don't have to write a plus sign up here or a negative sign up there. I don't need to write that because from both sides I'm getting 2 either way. You see what I'm saying? So I could write, as we were just doing, I could say the limit of this expression as x gets close to 3 from the high side is 2, and the limit as x gets close to 3 from the low side is 2. Therefore, it's 2. Yet when you put 3 in, there's a hole there and it breaks. Does that make sense? That's why that exists. So that's just some of the theory. And so I don't want to entirely skip chapter 2 because I just want you to think through this concept of things getting infinitely close and how it kind of breaks when they get infinitely close, and the theory behind that. I want you to have at least a sense of the tension here about infinity. You know, does Zeno's paradox, do you reach the wall? Well, yes, if you take infinitely many steps. We are literally touching infinity. We have to touch infinity to get the right answer. The fact that we can factor this is kind of our ability to touch infinity in this problem, but we're not always able to do that, as I think I illustrated with this last or semi-last, where did that go? This one. As I illustrated with this one, like what algebra are you going to do to that to be able to plug 16 in? And so we're sort of just stuck with saying, it looks like I'm getting 8 from both sides. And so I think it's 8, even though I can't actually know. There's a hole there. And so, you know, the idea is okay, well, there's a hole there. What if the actual number is, you know, off somewhere else? What if it looks like it's 8, but it actually isn't? It's 19 or something like that. Well, what mathematicians say is the limit is approaching it. It's approaching, in this example, it's approaching 2 from both sides. And so it's 2, even if it is off somewhere else and it's actually 5, still the limit is saying 2, and that's okay. That's enough. You're saying I'm getting infinitely close to 2, it's 2. Who cares if the actual point is off somewhere else? Who cares if there's a hole in it? The good thing is that real functions, as I said, that picture right there is actually 5 different functions. Well, of course you can make a hole in it, but this is not 5 different functions. It's just one. It's one function. It's right there. There's only one function here, so there's not going to be a hole in it. This is, in a sense, a continuous function. Well, it's not continuous because there's a hole in it. This is really 2. There's one on the bottom down here, and then you have to lift your pencil up, and then there's one over here. So that's why mathematicians kind of go off on all this, you know, weird business and talk about continuous, and they're just trying to do what lawyers do, which is make sure they're technically precise. And in doing so, they make it so that nobody can understand it, which is why I'm striking a balance between skipping chapter 2 and at least showing you a couple of things. So Monday, then we'll only do theory. We're never going to guess again. No more of this, you know, X is 1.999 business. Go ahead, Vale.
I was just going to ask about equations like tangent of X that have a bunch of asymptotes in them. Don't we have to be careful because of stuff like that?
Yeah, that's exactly right. And you may remember when you graphed cosecant of X and tangent of X that there actually are some it's only one equation, and yet it's broken into a whole bunch of graphs. And so if you happen to say, you know, I'd like to look at the slope, and you may remember even this simple graph. Here's an even simpler example of what Vale just said. If I said that, well, there's a pretty simple graph, 1 over X, maybe you remember that it ends up looking something like this, which makes it 2 totally separate graphs. And so if you foolishly say that you'd like to know the slope when X is equal to 0, that's going to be hard to do. Because when X is 0, where are you? Where are you on the graph? You're not on the graph. And so, in a sense, over here, it makes it look like the slope is really steep negatively, but over here, well, wait, it's also steep negatively over there. And so that ends up like tricky. Do you see what I'm saying? But what bothers me is, like, don't spend your time, ultimately, if you want to understand calculus, like, let's understand it simply first. And then if you want to go off into the weeds and ask about the slope at 0, fine, let's do it later. But does it make sense if I ask the slope, what's here, or here, or here, or here, or here? Those are all fine questions, and they have answers. Like, it's not complicated. So, you know, these represent 99% of the questions, and that they're the only ones that ever would come up in the real world. But true mathematicians say, well, what about that other 1%? When, you know, the one thing that you want to know is what happens where they don't meet. Well, that's not a continuous graph. There's a break there. And so unfortunately, in my opinion, calculus books will always address those technicalities, which makes it kind of impossible to read. It's really not that simple it's not that complicated of an idea. But anyway, I got to shut up and let you go. Stay after if you have anything that's bugging you about this, or if you want to talk about mountain biking or whatever. And otherwise, I'll you should be done. Your deadline is, well, now that you know calculus, what's your deadline for your assignment? It's 11:59 and 59 minutes and 59/60ths of a second. Like you have infinite
Sunday?
time, like Zeno's paradox. You have infinite time to get your assignment done, as long as you don't make it to midnight Sunday night. But there's infinite time between 11:59 and 11:60, right? There's infinite time there, so you have forever to get your assignment done. You're fine.
Could we talk more about the part that where you canceled out the thing? I still want to kind of talk about that.
Yeah. So again, feel free to check out from now on. I might erase this later, but let me ask you a question, Felix. Do you think 21/7 is equal to 3? Equal.
Sure.
Without question, like it doesn't bother you?
It doesn't bother me.
So it doesn't bother you because, ultimately because a mathematician would say, well, you can rewrite 21 as 7 times 3, right? And then why you don't so much cancel those. Those don't cancel. Why can those go away?
Equal to 1.
Because they're equal to 1, and 1 is considered. And by the way, there's a theoretical class in college that nearly destroyed my soul, where we talked about things like the multiplicative identity. In other words, 1 is the multiplicative identity, and that word identity means when you multiply by 1, that doesn't change it. In other words, it's kind of like saying I have 1 orange. Well, then just say you have an orange. Like you don't need the 1 anymore. And so, we went deeply into that theory. So it's just kind of weird if you question reality. How deeply do you want to question it? It's kind of like saying, is this a pen? Well, what's the definition of a pen? And I mean, it's one answer is like, yeah, let's move on.
Well, but right now you're using kind of a nice, pretty one that
Yeah.
actually works.
Sure. But my point is this any different? Why am I suddenly struggling? X minus 2. Has to be 7, 6. I'm struggling to make up a problem where this will reduce for some reason, but I think that will. No. This will. Why am I such an idiot all of a sudden? So easy, and yet I'm suddenly struggling. Is that any different than 21 divided by 7? No. The only real difference is we just haven't picked a number for x yet. Remember, x is not a letter. X is just a number. We haven't picked what it is yet. Right now, x is free to be 2 or 9 or 57 or 18. So this is still 21/7. It's just more than that, I guess you could say. I mean, aren't there other things that divide to 3? Like if I said, what's 15 divided by 5? Isn't that also another way to kind of write 3? Realistically, what I have here is kind of like that. Like this now could represent 21/7, or it could be 15/5. I haven't even limited it. But my point is it isn't any different if you take that top expression and you say, hey, look at that. It factors to x plus 3, x minus 2. And, like over here, hey, anything divided by itself is 1.
Well, that's kind of an assumption that we're making here, because there's extra kind of information that exists in that little setup that you have there that we kind of ignore if we just say, well, any number divided by itself is 1, unless it's 0 divided by 0. So we kind of destroy that information if we pretend that 0 also is part of that set of numbers that can just nicely turn into 1. So we would still have to have some kind of domain restriction on 2 in the new thing that we created when we removed that part.
Well, and I think that's the key. You're not right that there's a domain restriction. In other words, as it turns out in calculus, what we're sitting here doing is is we're kind of wishing we could plug in 2 for x. Does that make sense? That's not a restriction. It's just like, this is what we wish we could do. But when we try to do that, that creates a domain restriction. And that's just because that expression is messy. But if I come over here, which allows the prohibition against plugging 2 in, that prohibition goes away. So there isn't anything that says x can't be 2 here. We're just saying we wish we could let x be 2. And since we're able to change this expression into x plus 3, now we can. I mean, that's kind of the idea.
Well, surely,
In one sense, maybe what you're saying is, you know, like, hey, look, here's an improper fraction. And then you say, well, no, it isn't. That's a whole number. You know, what is 21/7? Is it an improper fraction or is it a whole number? I don't know. It depends what form you put it in, I guess. I don't know. I'm not totally sure how to.
I mean, surely if you're abstracting the problem into x's and, you know, variables, then it has to be, you know, because it's in this abstracted form, true for any x. So like if we want to like just take that problem there, put 2's for x's there, and then tell me that it also cancels, then that no longer works, right?
Yeah, and that's the idea of the whole, and that's why the theoretical side of this exists. In other words, you know, I am able to plug 2 in over here, and so in the end, I can actually say the slope is 5, right? And in a sense, what's bothering you is exactly the picture that I just drew. In other words, you're actually sitting here with an expression that looks like this with a hole in it, and so you're saying you can't put 2 in because if you do, you land right there, which is, it explodes, right? You're correct. So what mathematicians say is, okay, well, how about instead of going there, how about if we just say, let's get infinitely close? And what I said before about Zeno's paradox is why it's so profound. Because if you say you're going to get to the wall by taking infinitely many steps by cutting your distance by half, do you get to the wall? The answer is yes, you do, if you take infinitely many steps. If you stop, you don't. If you take 10 billion steps, you don't get there. If you take 50 billion steps, you don't get there. But if you take infinitely many steps, you actually do. And that's the concept of a limit. In other words, you're saying, okay, fine, you can't let x be 2, but what if we ask the question, what happens to that expression? I'm not going to rewrite it. What happens to that expression as you let it get, and notice in that statement right there is infinity. What if you let it get it infinitely close to the wall? Then it actually is 5. But you're sort of right to be bothered. Do you see what I'm saying? You're right to be bothered. But in the end, this is the algebraic reason why it's okay. Like you literally can plug it in because that particular expression doesn't have to live with the x minus 2 on the bottom. It doesn't have to stay there, just like the 7 in 21/7 doesn't have to stay there. There's an algebraic way to rewrite it. These are equal, totally equal. And so that gives us a way to actually plug 2 in. But you're sort of right. I mean, that's what's contained in this as x approaches 2 concept. That has to be infinitely close to 2. And if it is infinitely close to 2, then even though there's a hole there, we're still saying it makes it to 5. But it's bothering you, and then good for you, because this is not as simple as we might want it to be. If you're a true mathematician, there are things here to prove, if you will. And I would say honestly, you're more of a mathematician than I am, Felix, by being bothered by this as much as you are. So I say good for you. The only thing I would say, because I do find math interesting enough to, plus I just want to do a good job teaching, but like, I don't know, spend some more time pushing back against what I'm saying. But Zeno's paradox is the answer to this, and infinity is the answer to this question. You're getting infinitely close to 2, so it's 2. I'm sorry, you're getting infinitely close to 5, so it's 5. So I don't know. Try to either, maybe what I say is you're like, okay, I get it now, and you're done, or maybe you say, okay, well, I gotta formulate my problem more formally, and then, you know, hit me back with it. Keep thinking about it. And
All right.
and it may be that it may be that I ultimately don't have the answer, but it should bother you. I mean, that's why Zeno's paradox is actually still exists thousands of years later, because it's not to touch infinity. That's what we're doing here. We're touching infinity. And so you should say, well, we can't do, infinity is not a number, so I can't do this. And in the end, conceptually, that's what's bothering you, is more just, what do you mean? I mean, do you ever get there? Let me ask you, let me just say one more thing. What's your thoughts on this? 0.9 repeating. Is that equal to 1 or less than 1? What's your thought? What's your gut thought? You might change your mind later, but what's your gut reaction to that?
The hard part about this is that I've been told, and I guess kind of know because I've been told, that the answer is 1.
Mm-hmm.
But it still seems like kind of something that I just sort of accepted about, yeah, things.
Like somebody just told you it has to be true, so you're like, okay, I guess so. Well, let's play with this for a minute. And I'll show you how infinity is the answer to this. So let's say I'm trying to hunt down the number that is equal to, and I'm going to write a few of the 9s out. Actually, I'm not even going to put the bar over them. Let's just say ... meaning that never ends, right? Okay, that's pretty simple. And I made an equation out of it, and so I'm just sort of saying that's equal to a number, and the reason I used n is number, and I'm just kind of trying to figure out, what is that? Is it close to 1 or is it less than 1? And when I write it this way, every part of me wants to say that that's definitely less than 1, and I don't care how many 9s you put there, you're never going to make it to 1. Do you see how this is still Zeno's paradox? You still come up short of 1, and I feel that too. However, what if I took this as an equation? Now that it's an equation, I can do anything I want to both sides, right? Like I could add 1 to both sides, or I could subtract 6 from both sides, or I could multiply both sides by 10. So if I multiplied n by 10, I write n times 10, because there's no such thing as math with letters. What happens to the other side, though, if I multiply by 10? What's that equal to? You tell me.
9 point bunch of 9s.
9 point bunch of 9s, right? Now that I do that, the question is, and here's where the algebra is cool. If I take these two equations that I made, one made from the other, and I subtract them, 10 n's minus 1 n is not 10. 10 oranges minus 1 orange is 9 oranges. The interesting thing is what happens on the other side. The question is, up here, is there one less 9 on this one than there is down here? Do you understand what I mean by that? I mean, didn't we take 1 away? Didn't we take 1 9 and kind of put it over here? And so the question is there one less 9 on the top one than there is on the bottom one? What's your answer to that?
Well, but I guess there are, it's kind of hard to say that there's one less infinity 9s. I guess they're kind of the same either way.
That's exactly right. The answer, is there one less? The answer is no, if there are infinitely many 9s. The answer is yes, if there's a finite number of 9s. Now, the problem you and I have with this is infinity is not a number. And I don't care if you spent your entire life writing 9s out, like you went insane. A lot of times people go insane because of stuff like this. Like you just quit everything in your life and you're just going to write 9 down. Everywhere you go, every place you go, you just start writing 9s. The problem is you're never going to get to infinity. And you could even solicit all your friends in this, or every human that's ever walked the earth. We don't understand infinity. If there are infinitely many 9s and you take one of them away, you haven't lost any of them. And therefore, when you subtract 9.9 repeating minus 0.9 repeating, you get 9, and now n would be 9 over 9, which is 1. So the only reason that's 1, the only way that's 1 is if infinity means you never stop. But you and I just can't, we can't get our mind around that. We can't do infinity. We're finite creatures. We just can't, it's just crazy. I mean,
this is hurting my brain. I love it.
If you, I don't want to waste too much time if you've got like things to do, but
I'll
Could
tell you.
we-
I appreciate that.
could we go back to the problem again with the where we're canceling stuff out, I guess? Because it's not necessarily the infinity. I mean, obviously that's a whole confusing can of worms, but I had a problem with the division, really. I felt like the cancellation shouldn't work because when we're using x, we're kind of generalizing that any number will work for whatever operation we're doing. And I feel like if we like took out the x and put 2, then that same operation of trying to, to say that it turns into 1 and we could just get rid of it.
Mhm.
I feel like that operation kind of falls apart if we use 2.
Yeah, in other words, if you use 9 or 8 or 15 or any other number, then great. Like if I put 15 in there, 15 minus 2 is 13, 15 minus 2 is 13, 13 divided by 13 is 1. But you're saying since we are on our way to putting 2 in, then I'm really taking 0 divided by 0 and calling it 1, right?
Yeah, exactly.
I think that's a great question.
I actually don't think that
Keep in mind,
we shouldn't do this. I just think that like
yeah,
because it creates like an interesting description of the equation that we're looking at. Like it tells us like this limit, this really interesting thing about it.
yeah.
But I think that's kind of funny to me that we're almost ignoring this thing because we're not necessarily having to be totally precise with our algebra to still get something useful out of it.
I mean, one simple answer I have to this is we're not putting 2 in for x. Well, not yet. That's what I mean about the prohibition. Like, you're right, and in a sense, you're right. And I was less bothered by this than I am now, thanks to you, which I'm happy and unhappy about. In other words, what you're saying is you're free to call that, to cancel that out unless x is 2, right? Like that's what you want to add to your, that's what you want to add to this. So you want to say this is okay as long as x isn't 2, right? It's true if you
Yeah.
with your x. But again, what I'm really saying is, what did we say back here? We said, well, we're really not going to plug 2 in. We're going to plug in a number infinitely close to 2.
Well, you said that, and I trusted you, and then you stabbed me in the back by putting a 2 in as soon as we had x plus 3.
I think that's extremely well said. I totally agree with you. and I don't know. I mean, I'm sort of right with you here. You know what I'm saying? Like you're a future math major if you think that way. Yeah, I get it. I feel that tension, and I'm not sure. I'm not sure I have a great answer. And I appreciate that you stayed after to kind of further your case, if you will, because I feel that tension. I really do. I'm not sure what the ultimate way out of this is. But let me highlight something else. There was a guy named, shoot, I'll think of it in a minute. He's a famous philosopher, and all of a sudden I can't think of his name. But so, is that a pink coffee cup?
Sure looks like it.
But that's a pretty simple answer because I don't see coffee cups. Neither do you. What do you see?
Light, I guess.
Nice job. You see light. And so his argument was, his name's going to pop into my head in just a second. I can feel it. His argument was, you can never actually prove that's a coffee cup because what you have is what he called coffee cup sense datum. In other words, you have light bouncing off of a coffee cup and then it goes into your eyes, but all your eyes are actually really able to collect is light. And then you add the inference on top of that. Does that make sense?
Yeah.
And I've had this discussion with my wife because I'm more of I'm kind of like with the philosopher on that one. Like for all practical purposes, it's a coffee cup, but you'll never actually be able to prove that's one, that it actually is one. And his argument was kind of like, what if God, because philosophy and math always kind of turn into religion. What if God was like putting something there that, gave off, and it's not just tight, it's not just sight, it's also touch. Like I'm feeling it now, but am I touching a cup? No, I'm feeling pressure. You know what I'm saying? And so some part of it is just like, how do you want to go at this? Like when you look at the math problem, it's kind of like, well, for all intents and purposes, the limit is 5. For all intents and purposes, the limit, this is a coffee cup. But you actually, if you really want to be a person that questions reality, you kind of can. and I'm not saying like, my attitude is not even just that, like, you know, what's wrong with you? Just let it be a coffee cup and move on. You know, I mean, I get that argument, I really do. But I'm philosophical enough to say, well, you know, that's actually true. You kind of can't prove it. And mathematicians are sort of famous. Are you still there? Everybody's there, right?
Yeah, I'm still here.
Okay. Sometimes it freezes. And mathematicians are kind of famous for making statements. Like in geometry, if you study geometry, they'll say, okay, this is a straight line, a line. Like, what's a line? If I asked you that just question right now, I said, what is a line? You know, it's hard to define it without using another word that requires defining. Do you know what I'm saying? It's like a straight thing, you know, or it's like, well, okay, well, what's straight then? Like you're always referring to something that somebody has to count on. And so they'll say something like the definition of a line is a segment that's between a couple of points. And then they'll build their whole world on top of, let me give you a better example. How many angles, how many degrees would you say are in a triangle?
180.
180. And that's one of the assumptions that you make. But now I want you to think about the Earth for a second. So you're standing on the North Pole, okay, which is a ball. There's a ball, right? You're standing on the North Pole, and then you walk down to the equator. So you made a straight line, but you walked down to the equator, but the Earth forced you to curve as you got there. Does that make sense?
Yeah.
So, you know, it's like a curved straight line, if you will. Okay, cool. Now you walk along the equator for a while, which is also a straight line. You're walking in a straight line, but there again, the Earth is forcing you to curve. So I want you to think about, what angle did you just turn at? If you walked down from the top of the Earth and you hit the equator and then you turned and started walking, how many degrees did you just turn?
No idea.
Now think about that. You do know. Think about a ball. Do I have a ball around here? Yes, I do. I don't mean this to be a trick question. It just has a surprising answer. I'm going to move this over so I can see myself better, so I can see what you see. So if I start on the top of this ball, and I'll use the laces over here as the equator. If I start on the top of this ball and I walk down there and then I take off along the equator, what angle did I just take off? If you were to like turn that and look at it, what angle did I just take off at?
Oh, like a 90 degree.
That's exactly right. You just took off at 90 degrees, right? So, okay, fine, whatever, 90 degrees. Okay, then you cruise along the equator for a while, and then you decide to walk back up to the North Pole. Would you agree you just turned 90 degrees again?
Yeah.
So isn't that 180 degrees already?
Yeah.
And then you get back up to the top of the North Pole, and isn't there like an angle between those two paths you just took? And so isn't that angle like more than, isn't that triangle, the triangle that lives on a sphere, isn't the angles of that triangle more than 180? And the answer is, yep, it is. Like if the angles of a triangle adding up to 180 degrees, that's only true on a flat surface. If you're on a curved surface, that fact is no longer a fact anymore. And I guess that's kind of what I'm getting at. Like in the end, what mathematicians do is they say, okay, let's just say that this equation, when we let x approach 2, the y value approaches 5 from both sides, then we're saying that as you get infinitely close to 2, without it being 2, because like you said, in a sense, there's a prohibition against plugging 2 in. When you get infinitely close, it's approaching 5. And so although you can't put 2 in, when you get infinitely close, it's 5, then it's 5. In a sense, you might say that's actually an assumption. If you say the sum of the angles in a triangle is 180, you don't notice it, but you just made an assumption that you're in a flat world. If you're on a curved world, that's not true anymore. And so it's interesting, but what happens in math, but even in philosophy, is, you know, I'm going to choose to say that a coffee cup is what's causing all the coffee cup sense datum. Smells like a coffee cup, feels like a coffee cup, looks like a coffee cup. What are the other senses I forgot?
Yeah.
Sounds like one, right? A ding on it. Sounds like one.
With the geometry thing, that's non-Euclidean geometry, right?
That's exactly right. So it turns out that like you can invent an entire different geometry that's also internally consistent and true, but it lives on a curved surface, if you will. Spherical geometry, that's called it, because it doesn't actually have to just be on a sphere. Like, isn't there like just a curve? Like, what if it's just a random curve? That would be a totally different geometry. And so, yeah, you're right to question this stuff. And this is why math and philosophy kind of go hand in hand, or even math and religion, because it starts to turn into, like what's actually going on in the universe, and, what is infinity, and, what's actually causing those things, and, which is both cool and insanity causing, kind of both. I don't know. I would say ultimately, we have one guy in our department who's a real philosophical guy, and he wishes he didn't even have a body. He's told me this. He wishes he was a head in a box. That's exactly what he told me. And because he just loves to think and reason and philosophize. And so in one sense, I would say he's ran down this road, at least with respect to math. I don't know about philosophy and religion, but he's ran down this road further than I have. And I'd be interested to hear what he would be saying right now. If next time I see him, I'm going to try to word your conundrum a little bit, and I'm going to see if he has a way of, I don't know.
Yeah, I think it's really interesting what's going on here.
Yeah.
Like I don't like to like hold up the class like during it while it's happening, but I think that it was a little surprising at how few people were like not bothered by that, that step that was taken there, because I think it's really fascinating. I just wonder like how the person who kind of came up with this solution was willing to kind of do this to figure that out. But
yeah, well, and I would say it's a little bit, I mean, wouldn't you say most people are just going to say, dude, it's a coffee cup, move on. But the fact that you can't prove it, that's kind of interesting too. Or, the sum of the angles in a triangle are 180 degrees. Well, depends. I mean, if you make an assumption, that's true. If you make an assumption you're on the flat surface, it's true. And so, so I do want to say this, like, this is not the last time you're going to have a question of this type, right? I actually would prefer that you ask that during class, just because maybe other people aren't thinking that deeply. Do you know what I'm saying? And including me, like, you might ask questions that I don't ask. Now, here's an interesting question. Am I smarter than you? I want you to
maybe you probably know a heck of a lot more.
I would say with respect to math, I'm smarter than you, but I don't, but what is smartness? I'd say with respect to math, I know more than you. So I'd say what you said is actually really true. But you might be smarter than me in the sense that you think deeper, you solve problems faster, IQ has nothing to do with knowledge. You know that if you take an IQ test, you can know a lot, but IQ tests are based on like putting people in some kind of a philosophical or mathematical pickle and seeing how they, how quickly they can climb their way out of it. Like your synapses might connect faster, and you might work your way out of a novel problem faster than me. And in that respect, you might be smarter. Like you might be bothered more or have deeper questions kind of than the average person, which is really cool. Good for you. Go down that road. But I would like you to ask those kind of questions in class. And if you don't say, here, this is an interesting question to me, maybe we can discuss this after class, and then you mention it, you're already giving me permission to not hold the entire class up, because obviously most people just want to get this class the heck over with so they can be a veterinarian, right? It's one of the reasons I asked the questions I did at the start of this class, and they're perfectly welcome to do that, right? I have no problem with that. As I said, I feel like my first job is actually to help people get this class the heck over with that don't really care. But my job is also, I think, to inspire you to realize there's actually something here that's worth studying. This is not just a boring waste of time to get the heck over with. This is really cool, and it's more cool than Netflix, and more cool than video games, so to speak. It's really interesting, and it's neat, and I'd like everybody to see that. And if you don't ask the questions that occur to you like that, then maybe people won't think as deeply about this. And so, even if you ask the question, I say that's actually I'll either say that's pretty complicated, let's talk about it after class, or I'll say I have no idea, that's a great question, let's think about it more after class. But if you don't ask that stuff, then people don't. That's why I like to learn, and I like to learn with other people, because if I only have my own mind, I might not notice the interesting things there are to point out in the world. And so, good for you, good on you, I love it. I think it's totally cool. I expect to I expect to learn some. I've taught calculus a lot of times, and so I have to work harder to learn new things about it, if you will. But there's a lot I don't know about it. Do you understand that? Like, and when I say I don't know, like some of it is just I forgot. Like to find the slope of a curve, ultimately mathematicians say calling that taking the derivative. And so if I'm looking for the slope of tangent, like off the top of my head right now, I don't remember how to do that. But that's a memory thing. And there's some things that I use that I haven't proved or made or, done the hard work. And it's kind of what I said kind of near the end of class. Like, I gave you that problem that was x minus 16 over the square root of x minus 4. And what I don't want to do is show you how to do that one too quickly, because that takes the fun out of it. For some people, that's not fun at all. Please show me how to do that, because I want to be done, because I really don't like math that much, or these questions aren't interesting to me. That's okay. There's nothing wrong with that. For people that are really curious, if I tell you how to do that too quickly, that's kind of a bummer, because that's the equivalent, if you're ever been into exercise, at least you understand this, but it's like if some person's over there laying on the bench press and they're going, pushing that last one up, that last one, if they've done 10 of them and this is the 11th one, that last one is the one giving them the most strength by pushing it up. And if I walk over and go, oh my God, you're struggling, and I lift off of them, I've actually defeated the whole purpose that they were there for. Because when you put yourself up against a difficult problem, you are getting stronger by trying to figure it out. And so I feel like a weird spot as a teacher, because I neither want to, leave someone there to bench press 600 pounds while they're just going to die and they could never do it without helping them, nor do I want to lift a weight off somebody who actually could lift it, So that's just an interesting part of this job, I think.
Yeah, well, I think thanks a lot for being able to, chat a little bit with me after class, both of you guys. I'll probably be here again sometime, wasting more time with the questions.
Yeah.
You might regret giving me permission to ask all these kinds of things in class, but
I won't. I mean, you'll have to keep it short sometimes, because we have a place we need to go. And, as far as staying after class, if I need to go, I'll say, yeah, I can stay. I got like 20 minutes. And then we'll talk about it later. So ask away. To me, that's part of what makes this job fun. So you do need to understand that. I don't view my job as just like spitting out what I know and then, going away. I view it as as I said earlier in this class, I'm teaching you. I'm not teaching calculus. I'm teaching Felix and Becky. I mean, I'm wanting you guys to, grow as a human being. And so to whatever extent I can customize that, I'm totally willing to do it. So. All right, I'm gonna go get a new router because something's wrong with my system. So I'll see you guys Monday, yeah?
yeah, sounds good.
All right, bye-bye.